four different entropy interpretations, of which three are incomplete and one is complete. In 1865, Clausius postulated, that is, assumed entropy to exist in nature to make sense of, understand, and hence explain the experimental data regarding heat transfer phenomena. He used it to formulate his mathematical statement of the second law of thermodynamics, namely delta S total is greater than or equal to 0, where delta S total is the total change in entropy of the system and surroundings in question. He defined delta S system as Q reversible over T for an isothermal process. What exactly is this entropy? Clausius had no answer. He just felt forced to assume that there must be some property of substances that happen to indicate the pattern observed in experimental data. He decided to call it entropy, but had no clue as to what it was. Later, three different kinds of interpretations were offered. They are simple qualitative interpretations, but unfortunately incomplete in the sense that they help us understand the entropy change not in every situation but only in some selected situations. In 1882, Helmholtz interpreted entropy as a measure of the disorder of particles making up a given system. As the disorder of particles increases, the entropy of their collection also increases. It is known that entropy increases as we go from the solid to the liquid to the gaseous state of any given substance. According to kinetic theory of matter, the disorder of particles also increases as we go from the solid to the liquid to the gaseous state. Thus, the Helmholtz interpretation correctly explains our observations regarding the entropy of the physical states. It also helps us understand the decrease in entropy when the small molecules, water and carbon dioxide, combine together to form much bigger and more structured sugar molecules during the photosynthesis by plants, as well as when proteins are formed by the folding of their polypeptide chains comprising amino acid residues. Although there exists quite a bit of opposition to the above interpretation, it is not a wrong one, only incomplete. But it is definitely incorrect to say that entropy is a measure of disorder by ignoring the very important role of particles and hence apply it in the macroscopic world, such as to the disorder of objects in a room or to the bricks that are scattered on the ground as opposed to the wall made of those bricks. Although entropy is a property of a collection of particles as a whole, its value is always determined only by the nature of the particles. In 1949, Guggenheim advocated that entropy is a measure of the extent of energy dispersal or spreading out of energy in a given system. As the total energy of a system disperses more and more, its entropy keeps increasing. When the particles of a gas occupy a larger volume, the energy that they carry is dispersed to a greater extent than in a smaller volume. Therefore, the entropy increases. When all the particles of a system occupy the lowest allowed energy level, energy is the most concentrated and the entropy is zero. When more and more particles get excited to higher and higher energy levels, energy gets more and more dispersed and therefore entropy increases. Since the degree of excitation increases as the temperature increases, the entropy increases as temperature increases, as we always observe. The third interpretation is that entropy is a measure of the freedom of motion of particles in a system. The particles in a solid are restricted in their motion to just vibrational motion. When the solid changes to the liquid state, they execute short-range translational motion. In other words, the freedom of particle motion increases somewhat. When the liquid state changes to the gaseous state, the particles are able to exhibit long-range translational motion throughout the container, implying a much greater degree of freedom of motion. The known increase in entropy from solid to liquid to gaseous states of any substance is then taken to be due to the increase in the freedom of motion of the particles. This interpretation can also be employed to understand the decrease in entropy whenever atoms combine together to form molecules or formula units. For example, consider individual hydrogen atoms in a container. Each one is free to translate anywhere in the container. Now, let us say they bond together to form H2 molecules. Wherever one hydrogen atom in each molecule goes, the other has to necessarily follow suit. The second one, thus, has lost the earlier translational freedom. In fact, it changes into rotations and vibration, which are more restrictive in nature than translation. So, since the above three interpretations are incomplete, what is the proper interpretation of entropy that helps us make sense of entropy change in every situation? In 1896, Boltzmann published a mathematical connection between entropy and the probability of finding particles of a sample of matter in different energy states. In 1900, Planck modified it slightly and gave us the equation S equals K log W. The currently used one is S equals K ln W, where W represents the number of possible ways in which the particles of a given sample of matter can realize or exist in the macro state it is in. Each possible way is referred to as a microstate as opposed to the macro state. Thus, W is equal to the number of possible microstates. According to Boltzmann, a given macrostate at the macroscopic level of substances is always made up of a specific number of microstates at the microscopic level of particles. The particles of matter are distributed in space as well as among their allowed energy levels. These two kinds of particle distribution result in two types of entropy. Spatial distribution leads to positional or configurational entropy, and energy level distribution leads to thermal entropy. Let us consider both types one by one to illustrate the use of Boltzmann entropy equation. First, let us imagine a piece of metal that is made of just 3 atoms to keep the analysis simple enough. As mentioned earlier, in any solid, the particles execute only vibrational motion. If we assume simple harmonic motion, the allowed vibrational energies are 1/2 h nu, 3/2 h nu, 5/2 h nu, etc., with the gap between adjacent vibrational energy levels being h nu. H nu is referred to as one quantum of vibrational energy. To make the math simpler, it is generally assumed that E0 equals 0. Therefore, the allowed energies become 0, h nu, 2 h nu, 3 h nu, etc. At absolute zero of temperature, all the particles making up a solid are at the lowest allowed vibrational energy level. Thus, the 3 atoms making up our tiny sample are at the V equals 0 level. There is only one way in which this energy state can be realized by those particles. Thus, W equals 1 for this energy level distribution, yielding a value of 0 for the thermal entropy. Let us now say the solid absorbs 3 quanta of vibrational energy from the surroundings. That is, it gets heated and the temperature increases. In how many ways can this absorption of 3 quanta occur? One particle absorbing all 3 quanta is one way. One particle absorbing 2 quanta and another particle 1 quantum is the second way. Each particle absorbing 1 quantum is the third and last way. No other way is possible at all. Each of these 3 ways is referred to as a possible energy level distribution of the particles in question. we have represented them as D1, D2 and D3. How many microstates are possible for each of these possible distributions, and hence what is the total number of microstates possible for the given macrostate of n equal to 3 atoms and U equal to 3 quanta at the higher temperature. To carry out the analysis, let us label the 3 atoms in the solid as A, B and C. In the case of D1, the atom absorbing all 3 quanta can be A or B or C. Thus, there are 3 ways in which D1 can occur at the microscopic level. Therefore, the number of microstates W1 corresponding to D1 equals 3. For D2, the atom absorbing 2 quanta can be A or B or C, and that absorbing 1 quantum can be either of the remaining 2. Thus, there are 3 times 2 equal to 6 possible microstates. In the case of D3, since A, B and C are all in the same level, V equal to 1, there is only one way and W3 equals 1. Therefore, W total equals W1 plus W2 plus W3 equal to 10. And therefore, S equals KLN10 equal to 2.303 K. Thus, when the solid absorbs 3 quanta, its entropy increases from 0 at absolute 0 to 2.303 K at the new higher temperature. At any given moment, the solid is in one of these 10 microstates, constantly changing among them. It changes from one microstate to another through collisions among the atoms and the resulting exchanges of energy. A similar Boltzmann analysis shows that as temperature increases and hence as more and more excitations of particles occur, W always increases. Therefore, as the temperature increases, the thermal entropy always increases. The Boltzmann equation S equals KLNW sheds a deep insight into positional entropy also. To make the analysis simple enough, let us say that the initial macrostate of a system is a gas consisting of just 4 particles, which may be atoms or molecules, in the left compartment of a container, while the right compartment is empty. The 2 compartments are separated by 2 closely spaced partitions, the left one having a hole that can allow 1 particle to pass through at a time, but blocked by the partition on the right, which can be removed when desired. The volume of the left compartment is V1 and the volume of the whole container, namely the total volume of the left and right compartments together, is V2. Let us label the 4 particles as A, B, C and D. there is only one way in which this distribution can occur, with A, B, C, and D all being in the left compartment. Since the particles are indistinguishable, it does not matter which of the four particles on the left is where exactly in space in that compartment. W equals just 1 and SV1 equals KLN1 equal to 0. Now let us say we remove the partition on the right so that the hole on the left partition is no longer blocked and one particle at a time can pass through to the right compartment from the left. This results in various possible distributions corresponding to the larger final volume V2. It can be seen that there are totally 4 possible distributions, which we will refer to as D1 through D4. In D1, there are 3 particles on the left and 1 particle on the right due to the passage of just 1 particle. In D2, there are 2 particles on each side constituting a uniform distribution. In D3, there is 1 particle on the left and 3 particles on the right. Finally, in D4, all 4 particles are on the right, with the left compartment being empty. In the case of D1, it does not matter which of the 3 particles is exactly where in the left compartment. Since the 1 particle on the right can be either A, B, C or D, the number of possible microstates W1 equals 4. In the case of D2, corresponding to 2 particles on either side, the possibilities for, say, the left compartment are AB, AC, AD, BC, BD, and CD. Therefore, the number of possible microstates for D2, namely W2, equals 6. For D3, with 3 particles on the right and 1 on the left, W3 is the same as W1, since it does not matter if the 1 particle is on the left or on the right when it comes to the number of possible microstates. Thus, W3 also equals 4. For the last possible distribution, D4, with all 4 on the right, W4 equals 1, which is the same as for the initial state. Therefore, S1 equal to S3 equals KLN4 equal to 1.386 K. S2 equals KLN6 equal to 1.792 K. S4 equals KLN1 equal to 0. Thus, D2, namely the uniform distribution of particles, has the highest entropy among all possible distributions. A Boltzmann analysis indicates that this is always the case. According to the maximum entropy principle of thermodynamic theory, every system in nature tends to possess as maximum an entropy as possible. This explains why an equilibrium state always corresponds to a uniform distribution of particles as revealed by a uniform concentration and uniform pressure of gases and the uniform nature of the color of a colored solution such as blue copper 2 sulfate solution and yellow potassium chromate solution. In the final volume V2, WV2 equals 15 and SV2 equals KLN15 equal to 2.708 K. Thus, when V1 increases to V2 during expansion, SV1 equal to 0 increases to SV2 equal to 2.708 K. When our volume increases, entropy is always observed to increase also. Boltzmann analysis and his entropy equation help us understand this thoroughly. Boltzmann entropy equation also explains the three simple qualitative interpretations seen earlier. It is well known that there are always more ways to keep anything disorderly than orderly. That is, W increases as disorder increases and hence S increases. There's only one way in which anything can be perfectly orderly. That is, W equals 1 and hence S equals 0. Secondly, as the degree of freedom increases, W also increases and hence S increases. Complete restriction to do something implies it can be done in only one way. And thirdly, as the degree of excitation and hence energy dispersal increases, W also increases. Therefore, S increases. In every situation, when entropy changes, the Boltzmann equation can be employed to understand why the change is the way it is. Thus, it is the complete and quantitative interpretation, whereas the earlier three are incomplete qualitative ones. For many more details, including a discussion of Boltzmann distribution and an example analysis of the experimental data along the lines of Clausius, watch my video series, The Most Important but the Most Incompletely Understood Concept in All of Science, containing 5 parts. Also, see my book, Understanding Chemistry, for many details.